Good morning, everyone. Our goal today is to talk about one-to-one functions. So there are questions from those, and I want to do some more examples of that so that you can get the idea down and get the process of either proving that something is one-to-one or isn't one-to-one down. Just to give you the preview of sort of the rest of this big section, on Monday, we're going to talk about onto functions. On Monday, we'll be in the classroom. I do not remember what room it is in, somewhere in Olin. So we will come there. But before then, you need to have watched the videos on onto functions, and you need to have submitted questions on Katie, just like we have been doing here. And I will bring the questions and I will answer them there. Then on Wednesday, we'll finish we'll talk about the next two videos, I believe, which are bijections and inverse functions. And then for Friday, we'll finish off talking about everything with functions. And so for Friday, we'll talk about things involving functions and proofs. And all of that is in advance of Monday. We'll have the last test of the course. That is, except the final, which will be at the end of the course, of course. But we'll have the test on Monday. I will still have you do the test in LaTeX as you have been doing, so the test will not be significantly markedly different just because we're in person once we get to that. Okay, are there any questions about this schedule or bureaucratic stuff before I jump into questions that have been posed about one-to-one functions? Okay, so the first question is, if I have a function and it's a polynomial of degree strictly greater than 2, do I need to use the derivative to prove that it's one-to-one? And the answer is, it depends on context, but probably. It would have to be given to you in some other special way for you to do it without using the derivative. But as I said in the video, I'm not going to ask you any questions on the homework or on exams that require you to use something about the derivative. Someone asks if it's fair to equate the image of a function with the thing that in calculus we called the range. And yes, the image of a function is exactly what in calculus was called the range. And for whatever reason, mathematicians didn't like the word range, they liked the word image instead, so almost universally you'll see it called the image rather than the range. Someone asks if f of x equals x is one-to-one. And I'll note this function actually makes sense for any set, so this A can be whatever set you like, just a set. Then I can define this function from A to A that takes little a and sends it to little a. And so the question is this function always one-to-one? And so, in other words, what this is asking is it true that if f of x equals f of y, then x equals y? Well, it most certainly is true because f of x literally is x and f of y literally is y. So, in fact, f of x equals f of y quite literally means that x equals y. So yes, this is one-to-one. I should note, by the way, this function has a name. This is called the identity function on the set A. And this is something that will end up showing up a good bit in a number of courses. For example, abstract algebra, this will show up quite a bit. Okay, but the identity function is always one-to-one. And if you want to picture what the identity function would look like in terms of these dot diagrams that I'm fond of, well, all it would do, this would be A, this would be A, and it would just draw lines horizontally across. I want to note there's one more way one could interpret the function f of x equals x, and that way is also something which has a name. And so if A is a subset of B, then that comes together with a function, and I'm going to call this function iota, from A to B, that takes little a to little a. And this function is called the inclusion map. And so this is very much like the identity function, except with the note that the codomain doesn't need to be A. The codomain just needs to contain A. And so this is something you will also see quite often in many different places where you'll talk about the inclusion. And there's a pretty clear analog of this picture for if A is only a subset of B. Where the picture ends up looking like this. Okay. Let's pause for a second and ask, does the inclusion function have to be one-to-one? This thing I've just defined? And yes, it does, and the proof is identical to the proof we just used for the identity function. Namely, what do I need to show if I want to show that a function is one-to-one? Well, it's maybe worth writing that down again. To show that a function is one-to-one, we need to show that if I have two inputs that map to the same output, then they're the same input. So this is our boilerplate definition of one-to-one. And so, again, just like for the identity function that we looked at a moment ago, the inclusion function literally takes x to x and y to y. So if iota of x equals iota of y, that just literally means x equals y. Okay, someone asks if the function f from the empty set to b is 1 to 1. Okay. Great question. And so I think the important thing here is to think about what is the negation of saying a function is 1 to 1. Okay. So f, I should say, is not 1 to 1 if there exist x and y in A such that f of x equals f of y and x is not equal to y. I should say f from A to B. Okay. And again, all I did here was just apply what we learned in the first part of the class about how to negate something to negate the definition I wrote up here. So this for all x, y becomes there exist x and y, and this if f of x equals f of y becomes f of x equals f of y, and the then becomes x is not equal to y. Now, I claim, actually, you don't have to read that far into this statement to decide that the answer is yes, the function f from the empty set to the set B is 1 to 1. Namely, as soon as you get to this blue underlined part, then you know this function has to be 1 to 1. Why? Because in order for it not to be 1 to 1, I would need to find elements of the empty set with some property, but I actually don't even care what the property is, because as soon as in order to show something is not 1 to 1, I need to write down elements of the empty set, well, that can't happen. Now, related to this is actually a slightly stronger statement. So here is a proposition for you. So the posed question, I should say, the question posed to me was, is it true that every function from the empty set is 1 to 1? And the answer is yes, but I can go one step further and say, also, if the size of the domain is 1, also the function is definitely 1 to 1. And you can see that this proposition has to be true, again, just by looking at what it means to not be 1 to 1. Okay. Namely, in order for a function to not be 1 to 1, there have to exist elements x and y in the domain such that f of x equals f of y, and this is the important part, x is not equal to y. And so if the size of the domain is 1, then I can't even, never mind this f of x equals f of y part. If the size of the domain is 1, I can't even write down elements x and y such that x is not equal to y. Okay, any questions about this so far? Okay, the next question is, if a function's domain is larger than its codomain, can we just use the pigeonhole principle to show that the function cannot possibly be one-to-one? And the answer is yes, provided that by larger you mean they're both finite. So, for example, minus the empty set to, and so I want this 1 through 10, cross 1 through 10, cross 1 through 10, and let's send it to, and then so we could send it to, for example, we send to set A to the min element of A, the max element of A, and the size of A. And I ask if this is one-to-one. Well, it's very possible to come up with two things that map to the same place. But you could also use the pigeonhole principle. Okay. And here's how. The size of the domain is, well, it's 2 to the 10th minus 1. Right? I started with a power set of 1 through 10. So that would have size 2 to the 10th. But I took away the empty set. So that is 2 to the 10th minus 1. That's 1,023. But the size of the codomain is only 10 times 10 times 10. Which is 1,000. So, by the pigeonhole principle, there doesn't even exist a one-to-one function from this domain to this codomain. Okay, so in particular, this one definitely isn't. Okay. And that's a perfectly acceptable proof. You do not need to write down an example if you have some other theorem you can quote that tells you this. Now, I'll note we don't know anything about sizes of infinite sets as of yet, so there's no such thing as like, oh, this infinite set is bigger than this infinite set. That we cannot do anything with. But for finite sets, you can definitely apply the pigeonhole principle. Okay. Reminder, though, the pigeonhole principle only works the one way. If I reversed it and I instead wrote down a function in the other direction, So let's say I define f from, or maybe g this time, from this Cartesian product to that power set and let's say I take the triple ABC and I send it to the set ABC. Well, in this instance, the size of the domain of G is 1,000. The size of the codomain of G is 1,023. And so what does the Pigeonhole Principle say? So the Pigeonhole Principle says there exists a one-to-one function with this domain and this codomain. Now, what bearing does that have on whether this function is one-to-one or not? Okay, so to summarize, there exists a one-to-one function from this set to this set. This is a function from this set to this set. What does that tell me? And the answer is absolutely nothing, right? The fact that there exists one does not tell me that this particular thing is one. Right. So here, the Pigeonhole Principle has no conclusion. So here's an easy way to remember this. The Pigeonhole Principle, any of the versions I've given you so far or will give you, the Pigeonhole Principle can't prove that a function is one-to-one, or is onto, which will be the next video. It can only show that it doesn't happen. And that's because the Pigeonhole Principle is about the existence of one-to-one functions with this particular property. If there does not exist a function with this particular property, then, well, every function from that set to the other set, they're all not one-to-one. But if instead you look at it the other direction, if you look at a case like this where the domain has size less than or equal to the codomain, all the Pigeonhole Principle says is, well, there's some one-to-one function from G, from the domain of G to the codomain of G, but doesn't tell me whether this one is one or not. Okay, so when I go to ask, is this function one-to-one, I have to actually look at it. Okay, so does this make sense why the Pigeonhole Principle can be used to answer this question right away without writing down elements, but cannot be used to answer this question at all? But this is actually a good point for us to pause. So since the pigeonhole principle doesn't work, why don't I give you a bit of time to answer, is this one-to-one? And once you've answered that, you can also go back and look at this function I wrote down up here. We know it's not one-to-one, so there must be two elements that map to the same place. What's an example of two elements that map to the same place under this function I wrote down up here? So I'll give you a few minutes to look at both of those questions. So again, the questions are, is this function one-to-one? And what are two elements of the domain here that are different but map to the same element? All right, I'll give you a few minutes to think about those questions, and then we'll talk about them. Okay, so let's take a look at these. So for G, is G one-to-one? see 2 votes for no. Can we give an example of 2 things in the domain that map to the same element in the codomain, even though they're different? One, two, two, and 112. That works. So yeah, if I look at what happens when I take G of 1, 2, 2, well, by my formula, that's going to turn that into the set 1, 2, 2. Except the set 1, 2, 2, keep in mind, is the same thing as the set 1, 2. In the same way, G of 1, 1, 2 will be the set 1, 1, 2, except that's the same thing as the set 1, 2. Okay. And so here are 2 elements. I'll call them X and Y just to mirror the definition. Equals 1, 1, 2, such that X and Y are in the domain. G of X is equal to G of Y, as we've just shown, and X is not equal to Y. Okay. And that's exactly what our definition above said we need to show in order to show that G is not 1 to 1. In particular, this shows you that if you are skeptical of my claim that the pigeonhole principle definitely doesn't tell you that this function's 1 to 1, well, the pigeonhole principle better not have told you that this function's 1 to 1 because it isn't 1 to 1. Okay. And so, even though the size of the domain is strictly smaller than the size of the codomain, this function still fails to be 1 to 1. Okay, questions about that? Okay, how about the other question I asked? So, we know this first function is not 1 to 1, which means there have to be 2 things that get mapped to the same element under this function. Can someone give me 2 things that map to the same element under this function? One, 3, 5, and 1, 4, 5. That is very much the kind of example I would have given. So if we look at this, we can take here X to be the set 1, 3, 5, Y to be the set 1, 4, 5. And you absolutely don't have to call these things X and Y if you don't want to. I'm just trying to make them mirror the way I wrote the definition of 1 to 1 today. But if I write down X is this set and Y is this set, then f of X is the minimum element, the maximum element, and the size. And likewise, f of Y is the minimum element, the maximum element, and the size. So in fact, both of these are the ordered triple 1, 5, 3, even though X is not equal to Y. So if you like, you can view this as an alternative proof that this function's not one-to-one. Okay. Oh, I guess I have this sheet of paper from before. So with that, we can go to questions about the homework. There were some of these. So someone wanted to talk about 57G and F. Yeah, so 57F. Sorry, I'm looking at the wrong question. It would help if I looked at the right question. So 57F. 57, by the way, is the question that asked you to write down examples of functions with a given domain and codomain. So in 57F, it wants you to choose the domain R and the codomain, the interval from -1 to 1. And so I want to write down a function here that inputs an element of R and outputs a number in the closed interval from -1 to 1. Is there a natural choice for anyone, like any simple familiar function that would do this? Yeah, so that's what I would have chosen as well. I would have chosen x goes to sine of x. Remember, one of the key things about sine is that sine is always between -1 and 1, and so that exactly means that sine happens to map into this interval, and sine definitely isn't constant. This is probably the question I was asked about the most, which is about how am I supposed to start with an integer and end up with a prime? And I think the key here that is worth reiterating is that your function does not have to look like an algebraic formula. So if you try something like send n to n squared plus n plus 41 or something, it is not going to work super well. Indeed, no one knows a reasonable formula that always outputs primes that looks like one of those sort of algebraic things. But I certainly know that every integer is related to primes. Namely, every integer factors into primes. And so I would do, if I were doing this, I would say send n to the largest prime factor of n. And that is certainly a reasonable, well-defined function that will take every integer to a prime number. And in fact, once you see something like this, you can probably guess this is why there's a greater than or equal to 2 here on the z, because 1 doesn't have any prime factors. So if I included 1 here as opposed to starting at 2, then I would need to fudge it in some way to make it so that I didn't have to deal with 1. Not that I'm saying you couldn't do that, just to say it would make the question a little more annoying. Okay. There is also a request to do 56E. So I want to go back and remind you what 56 was about. So 56 was all about this construction xi of s, which was defined to be the set of x, y in the power set, cross the power set. So this is a pair of subsets of S with the property that X intersect Y is not the empty set. And so what 56E asked us to show is that the size of xi of S is always at least as big as the size of S for S finite. Okay. And so in the hint, I'm pretty explicit that what you have to do here is to write down the elements of S. And so say, let's let S be a finite set. Size of S, let's call it N. And then let's just go ahead and name all of the elements of S. And so somehow I have to use these elements to write down n different elements of xi of S. And that will show me that, well, S has n elements. That will show me that xi of S has at least n elements. I think the easiest way to do this, and there are a bunch to choose from, but I think the nicest way to do this is to take the list x1, comma, x1, comma, x2, comma, x2, and this is then a list of n different elements of xi of S. So, in particular, the size of xi of S is at least as big as n. Okay, and that's what we were asked for. Okay. Let's talk about 57G. Oh, we already talked about 57G. And then someone asks about the thing I talk about in 60D. Namely, they're just asking about what does this symbol mean. Okay, so this is the floor function. And what the floor function does is to give you the biggest integer that is less than or equal to this number. Okay. It's also sometimes called the greatest integer function, although when people call it the greatest integer function, they have a tendency to write it like this instead, or some variation thereof. The reason why I like this version better than this is that you also get with it the ceiling function, which does the same thing except gives you the integer that's bigger instead of the integer that's smaller. But the practical effect of this is that you just throw away the decimals. So when you take something like the floor of pi, you just get 3. And the only technicality to worry about is that if you take the floor of an integer, you get that integer back. So this is just an example of a reasonable function that goes from the reals to the integers. So it is a natural function to come up in examples of these sorts of things. Okay, are there any more questions about the homework or anything we've said so far? I have lots of examples that I can give you, but if there's any more questions, I want to answer those before we jump too deep into examples. Okay, seems like people are happy with this, so let's do some examples of functions that either are or are not one-to-one. So I'm going to write down some functions, and after I write down each function, I'll give you a bit of time to think about it. And so the goal is to either prove the function isn't one-to-one or prove the function is one-to-one. Okay, so I'll give you a little bit of time to look at this and either write down, again, a proof that this function is one-to-one or a proof that this function is not one-to-one. One of those things has to be true. And so let's just figure out which one it is. Okay, so I'll give you a couple minutes to look at that, and then we'll talk about it. Okay, so right off the bat, we have an example of a function that is one-to-one. Okay. And reminder, that's kind of the thing we hope we don't have to deal with, because when a function is one-to-one, we have to write down a proof that for every x and y, blah, 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 as opposed to just giving an example of two inputs that map to the same output. Okay. At first, you may well be inclined to think that it's not going to be one-to-one, by the way, because you see this x squared here and think, oh, this is going to be a parabola. And famously, parabolas are not one-to-one because of their shape. But this one does actually end up being one-to-one because of the domain that has been chosen. So let's see what a proof that this is one-to-one looks like. Okay, so again, I need to show that if I start with x and y in the domain, and it so happens that they map to the same place, I need to show that that tells me that, in fact, x and y are equal. Okay. So let's write this out. So thus, x squared plus x plus 1 equals y squared plus y plus 1. So let's subtract everything over. X squared minus y squared plus x minus y equals 0. And so I get to do some factoring. So this is going to be x plus y times x minus y plus x minus y is equal to 0. And so now this actually says x plus y plus 1 times x minus y is equal to 0. Okay, and so all I did here, by the way, was to factor out an x minus y from this. This is 1 times x minus y. This is x plus y times x minus y. So I wrote it out like that. And so now that I have a product being equal to 0, as I always say, all the way back to calculus, once I have a product equal to 0, I'm happy because I can split it up into an OR statement. So x plus y plus 1 equals 0, or x minus y equals 0. I claim in this instance I actually know which one it is. And the reason for that is that because of my choice of domain, this can never happen. So because x and y are each greater than or equal to 0, x plus y plus 1 is strictly greater than 0, so it's not equal to 0. And so I have an or here where it is this or that, but I also have not this, so therefore that. Okay, and that, once I have x minus y equals 0, I add y to both sides. That gives me x equals y, and then I am done. Okay. Questions about this? So there is an appealing idea of trying to use the derivative, but I think if you try and use the derivative here, because the derivative of this function is not always positive, you then have to hunt down exactly what it tells you if the derivative of a function is positive on an interval. And so that, I think, gets a little more convoluted. You can absolutely do it with the right theorem about derivatives and sines and intervals, but you probably need a pretty clear statement of that theorem in order to make it work. And probably you don't want to try and rely on that. That would be my advice. So the intuition is fine, and I'm certain with the correct background of theorems you could make it work, but I don't think you can just quote stuff from Calc 1 to get there. Other questions? Okay, so how about this? Well, I probably have a pretty good idea that this is not going to be one-to-one. Because, again, this is going to be shaped like a parabola. And now the domain is all of R. But what I want to point out here is that the work we just did actually tells us exactly what all of the pairs of x and y where g of x equals g of y look like. Namely, all of them have to come from this x plus y plus 1 equals 0 business. So the simplest case is probably if x is 1 and y is 0. Sorry, if x is minus 1 and y is 0. And so g of minus 1 is 1 and g of 0 is 1. So g is not 1-to-1. But this will give you a whole factory of examples. And so my point here is really, sometimes you know a function's not 1-to-1, but it's not super easy to come up with a pair of things that map to the same place. You can find that pair of things often just by setting the function at x equal to the function at y, as we just did, and solving it, and actually using solving it to find the pair of x and y that make these things equal without making x equal to y. So that, for example, works here. Okay, so let me give you a variation on this question, and I'll give you some time to think about it again. So let's do f from z to z that takes n to 2n squared minus 11n plus 4. And I will give you a few minutes to look at this and decide whether you believe this is 1-to-1 or not. Okay. Do people have a proposal? Do they believe this is one-to-one, or do they believe it's not one-to-one? Or are they uncertain? Okay, so someone observes if this were R to R, it would definitely not be one-to-one. Okay. Uh, and I completely agree. If this were R to R, the graph would have to look like a parabola of some sort, and that automatically means there's going to be a y value like this one, where the same output occurs more than once. Okay. So if this were R to R, I would definitely agree that this is not one-to-one. So then the question is this version one-to-one? Has somehow the fact that I've dropped out all of the real numbers between the integers, could this somehow work out to be one-to-one? Okay. So someone nominates not one-to-one. Do we have a proof that this is not one-to-one? Like, do we have two inputs that go to the same output? Okay, so the nice thing here is if we're not sure after looking, we actually have to do the same thing, whether the answer is going to turn out to be yes or no. Okay. Namely, the thing we're going to have to do is set f of x equal to f of y. And that's going to lead to one of two places. Either I'm somehow going to solve that and decide that, in fact, x and y have to be equal, in which case it will be one-to-one. Or I'll solve that and find out that there are actually x and y that are not equal, but that go to the same place. So let's just try solving f of x equals f of y and see where that takes us. So let's be careful here. So this is 2 times x plus y times x minus y minus 11 times x minus y. Okay. I can again factor out an x minus y. And so this will give me 2x plus 2y minus 11. Now, I'll note whenever you do this whole business where you set f of x equal to f of y, if these things are numbers, you're always going to be able to ultimately factor out x minus y. And the reason for that is that definitely every x that... Sorry, let me phrase that again. Every time x and y are equal, that is definitely a solution to the equation f of x equals f of y. And so you're always going to be able to pull out a factor of x minus y when you're talking about numbers here. So this should not be surprising. And so in a sense, what happens is that you split this up into the times where f of x equals f of y because x and y are equal. That's this factor. And then the other factor here ends up being the quote-unquote interesting times that f of x and f of y are equal. So the times where x and y are not equal. And so, having now done this, we should be able to either find x and y, where f of x is equal to f of y even though x is not equal to y, or we should see a reason why that can't happen. So I want you to look at this for a little bit more time and see if you can tell me either how this gives me an x and a y where f of x equals f of y even though x and y are not equal, or how this shows me that this function really is one-to-one. And once you have an idea, you can put a sketch in the chat. Okay, I see someone has moved into the camp of believing now that it is one-to-one. Yes. So that is an excellent way to see this. So if x is not equal to y, then what does that mean? Well, then 2x plus 2y minus 11 is 0. And so as May suggests, I can solve this for x plus y, which would give me 2x plus 2y equals 11. So x plus y equals 11 halves. Except as noted, if x and y are integers, this can't be true, because the sum of two integers would be an integer. An alternative way to see the same thing, if you want, is to look at this quantity and think about its parity. 2x is definitely even. 2y is definitely even. 11 is definitely odd. And so this number that I have circled in the orange that looks way too much like the red, this number is definitely odd, because even plus odd is odd. And at first that might seem not immediately helpful, but actually one thing I definitely know about odd numbers is that odd numbers are not 0. And so, like in the last example we did, where sort of the key step was to note that because x and y were in the interval 0, 5, x plus y plus 1 could not be 0. One way to write up the proof that this thing is 1 to 1 is to say that because x and y are integers, this thing is odd, so this thing's definitely not 0, and so therefore x minus y is 0. Okay, and so x is equal to y, and so this function is 1 to 1. Okay, and so just to finish this up, so 2x plus 2y minus 11 is not 0, so x minus y is 0, so x is equal to y. Okay, questions about that? Okay, let me give you two of these that involve piecewise functions, and I'll let you have some time to think about them. For x greater than 4. Okay, so I'll give you a few minutes to look at both of these. As a hint, one of them is 1 to 1 and one of them is not 1 to 1. And then we'll come back and we'll talk about how to write up these kinds of proofs in the case that you're looking at something that's like a piecewise function. Okay, so let's talk about these. So really, this chapter is all about taking all of the proof methods that we learned in the last chapter and figuring out how to apply them in a variety of circumstances to apply these definitions. So for example, to show that a function is one-to-one or is not one-to-one, and all of these sorts of things. Now, one method that you can be almost guaranteed is going to show up if you've got a piecewise function like this is you're almost certainly going to need to use proof by cases. In fact, we've seen that lots of times before, but probably there's going to need to be proofs by cases involved when you're proving something is one-to-one out of one of these piecewise functions like this. Okay. Now, fortunately, one of these isn't one-to-one, so one of these we can just write down an example to show that it's not one-to-one. Does anyone have a nominee of which of these is not one-to-one? Okay. F is not one-to-one. Okay. And so I think there's a way to sort of eyeball this, which is to sort of mentally think about what outputs you're getting from each of these pieces. Okay. And I'm not claiming that this is rigorous. It is definitely not in any way rigorous, but it will get you to the answer. Namely, if x is less than or equal to 4, what numbers do I get out of this? Well, I get numbers between minus infinity and 9. If x is greater than 4, what sorts of numbers do I get out of 3x minus 7? Well, I get out numbers that go from 2 up to infinity. Okay. And one thing that is worth noticing, there is some overlap between these two intervals. Okay. So, for example, let's say 5 is in both of these things. And so it should be the case that it is possible to get 5 out of both of these. Okay. And so when I actually go to write down the proof, I can sort of intuit that I'm supposed to show, and I just picked 5 because it's one of the things that's in both of these intervals. Feel free to pick something else. But f of 2 is definitely 5. But also f of, well, let's see, what would I need in order to make 3x minus 10 equal to 5? Well, I need x equals 5. Right, that I just mentally solved 3x minus 10 equals 5. Okay. And so f is not one-to-one, and my proof here is that f of 2 equals f of 5, but 2 is not equal to 5. Okay. Now, you're unlikely to just sort of like find this pair just by plugging in things at random. But once you sort of figure out what's going on, just even in a rough, intuitive sense, then you sort of know where to look, and then you can write down this very concise proof that this thing is not one-to-one. Okay, so that means that we need to prove that G is one-to-one. Okay, so we know the structure, so we're going to suppose x and y are in Z, and g of x is equal to g of y. Okay. And as foretold, we need to use cases. Okay, now here's a hint for all of these piecewise one-to-one sorts of things. People are always inclined when dealing with piecewise functions to do cases about the input. But actually, it's not the input that we need to do cases on. It's the output. Okay. And why is that? It's because g of x equals g of y is the thing I'm looking at. And so my cases actually need to be on g of x and g of y. So my first case here is going to be that g of x equals g of y is even. If g of x equals g of y is even, what does that tell me about x and y? Well, what's the only way to get an even number out of this function? Right. Put an odd number in, right? 2n plus 1 is definitely odd. And by the way, having made it to this point in the class, you do not have to like write out a long spiel. I will accept it if you tell me 2n plus 1 is definitely odd at this point. But 2n plus 1 is definitely odd. So if g of x and g of y are even, that tells me that both x and y have to have come out of this part. And so that tells me that x and y are odd. Now, at this point, there's an almost Pavlovian response that since I know x and y are odd, I'm supposed to pick k and l such that x is 2k plus 1 and y is 2l plus 1. But I actually don't even have to do that. Because now that I know x and y are odd, I know what g of x and g of y are. Namely, g of x is 2x, and g of y is 2y. Okay. And the reason for that is that as soon as x and y are odd, then when I look at my description, the input is odd, so I go to this row, and my output is twice the input. So that tells me that 2x is equal to 2y, and so x is equal to y. Great. And as you might guess, my other case is going to be very similar. Namely, my other case here is going to be that g of x equals g of y is odd. In which case, by the structure of G, that tells me that x and y are even. And so since x and y are even, that tells me that g of x is 2x plus 1, and g of y is 2y plus 1. And so what that tells me is that 2x plus 1 equals 2y plus 1. So 2x equals 2y. And finally, x equals y. Okay, now we've completed both cases. Certainly, since g of x equals g of y, it's an integer. So certainly it's even or odd. So we're done. Both cases, and so we're done the proof. The biggest lesson here is that if you need to do cases on a one-to-one proof, you never want the cases to be on the inputs. You want the cases to be on the outputs. Okay. And so it's not always immediately obvious if you think about it, but anytime you're proving something is one-to-one and you've assumed g of x is equal to g of y, this is a number, and you can use that number in your proof, or an element of whatever this is. Okay. So generally, your default, if you need to do cases, is to do cases on this. Okay, questions about that? Okay, so let me write down a variety of these things that are going to involve Cartesian products or Cartesian product-like things. So here is a sheet of these. Most of these are not one-to-one, by the way. P and Q here in lowest terms. Okay. Okay, so I believe, by the way, exactly one of these is 1-to-1. So you should be able to knock at least a number of these out pretty quickly by looking for pairs of inputs that map to the same output. But I'll go ahead and give you until 12:45 to look at these. Try and wrap your head around what each of these functions is doing, and then try and either come up with an example of a pair of inputs that map to the same output, or, again, a proof that the function is 1-to-1. Alrighty, welcome back. So I believe I said one of these is 1-to-1. Which of these is 1-to-1? Does anyone have a nominee? I agree. H is the one that is 1-to-1. So let's first write down the proof that H is 1-to-1, and then we'll write down proofs that the others are not. Okay, so let's suppose that h of x equals h of y. And so what does that tell me? That tells me that x squared x cubed equals y squared y cubed. So in other words, x squared equals y squared, and x cubed equals y cubed. Okay, now be super careful here because as we have talked about numerous times in the videos, I definitely can't just take square roots and be done with it. So I have to be a little bit more careful here. And there are a lot of ways to handle that a little bit more careful. One way, I think, is to realize that if you divide this equation by this equation, then you end up with x equals y. And so if I want to divide an equation by another equation, the only thing I have to check is that I'm not dividing by 0. Okay. And so I want to note, if x squared equals y squared equals 0, then it is certainly the case that if you square a number and get 0, that number was 0. So if, in fact, this equation is 0 equals 0, that tells me that both x and y are 0 automatically. But in every other event, we can divide the equations. And what that will end up giving us is x cubed divided by x squared equals y cubed divided by y squared. And that's the same thing as saying that x equals y. And then so we're done. Okay, questions about that? Okay, so what remains then is to, for each of these functions, write down a pair of inputs that map to the same output. So let's do f first. So for f, what's a pair of inputs that go to the same output? 3 and a third, right. So if I take f of 3, that's the same thing as f of a third. Because remember, if I go to write 3 as a fraction in lowest terms, it's 3 over 1. And so 3 plus 1 and 1 plus 3 are the same number. Okay, so that definitely works. How about for G? What are two things that map to the same place for G? One and minus one, right. I think G is actually the hardest of these to find the example of. But if you look at this t cubed minus t, you might raise an eyebrow at the fact that t cubed minus t is in fact exactly t times t squared minus 1. And so if you choose a t that will make t squared minus 1 0, it will in fact also make t cubed minus t 0. And so namely that means plus and minus 1 are the options. Okay. In fact, for G, this is literally the only example that will show you that G is not 1-to-1. G is otherwise 1-to-1. So if you're going to show that G is not 1-to-1, you have to eventually find a way to find that G of 1 and G of minus 1 are equal. What about K? I think there's one observation you can make about K that helps an awful lot. So if someone wants to share either the observation about K or just an example, I will be happy to see them. I don't think it is. I think it's missing a 2. And so what is it that's special about that? And so someone says K of 1, 2 equals K of 2, 1, okay, which is certainly true. And now, I actually claim if you look at the formula for K, you can actually tell that K of 1, 2 is going to equal K of 2, 1 without even plugging it in. And the reason for that is that this formula, both this coordinate and this coordinate, they're both symmetric in x and y. Meaning that if you swapped x and y, you'd get exactly the same function. Okay. So this whole thing, this is symmetric in x and y. Okay. And so that means 1, 2, and 2, 1 are going to give you the same thing, but so are 3, 7, or 8, 16, or 9, 121, and 121, 9. Any pair of inputs, if you swap them, will give you the same output because of the structure of the way this is written. Okay, and so last up, how about L? 4, 1, and 1, 3. That sounds right. So L of 4, 1 is 16 plus 7 is 23. And L of 1, 3 is 2 plus 21, which also is 23. And so that is another example. Okay. Now, I want to note, really, in a way, this list is in fact a proof that these 4 functions are not one-to-one, and it's not all that many terribly many characters long, whereas we had this whole like proof thing to show that this one is one-to-one. And yet, I bet it took way more of your time to find all of these counterexamples than it did to write the proof that this thing was one-to-one once you suspected it was the one that was one-to-one. Acknowledging that each of these things I've written down is a counterexample to show you that the thing is not one-to-one is not quite the same as coming up with them. And each of these probably had some key insight. So for this one, that key insight was that this thing is symmetric in x and y. For this one, the key insight is this t squared minus 1 floating around in both of the pieces. For this one, that key insight is actually that this question is really, at the end of the day, a question about the mod 7 buckets. Because the only place it makes any sense to look for examples of things having the same output is things where these things end up in the same bucket mod 7. So that is, in this particular instance, we ended up finding things where they both end up in the 7k plus 2 bucket. But it's not worth looking for things if they don't end up in the same bucket mod 7, and so that lets you sort of stumble upon this. Okay. So again, when you're looking at these sorts of questions, remember it might take you a while to come up with these examples, and you might have to actually do some digging and thinking about the structure depending on the question in order to come up with these. All right, I will post the homework for next week, as well as question things later today, so you can dive into the homework on one-to-one functions. I realize I had not posted it yet. That was an oops on my part. But I will post that later today. Remember, on Monday, we're meeting in Olin 208, so you can join me there, masked and all that good stuff. The room is pretty big, and there are 11 of us, so we should not have too much trouble managing to stay our various appropriate amounts of space apart. If you have any questions or concerns about any of that, definitely let me know. But if not, I will see you on Monday, and have a wonderful weekend.